Hey everybody, and welcome to our third calculus lecture. Before I get this lecture going in earnest, I'd like to mention something that I didn't talk about in the second lecture, and I kind of wish I had. It had to do with the arithmetic properties of the exponential function. There's one thing that I didn't tell you that in retrospect I kind of wish I had. I gave 6 arithmetic properties of the exponential function. And there is a 7th property. Maybe it's no big deal, and then again, maybe it is. I probably should have mentioned it anyway since this is new to us. And here's the property that I'd like you to go back and add to your lists, please. That 7th property is the natural log of e is equal to 1. That's something that we should know, and it's something that's easily derived from the other properties of the exponential and logarithmic functions. As a matter of fact, since I'm wasting time right now, let me waste a little bit more just to justify this statement. The natural log of e, we can write that as the natural log of e to the first power. E to the first power is just e. And now this makes sense because natural log and e undo each other. And if we evaluate the natural log at e raised to a power, what do we get back? Yep, that's right. We get the exponent. So this is why the natural log of e equals 1. There's a simple explanation, and I'm sure we can follow the logic of this perfectly, but it just might have been something that didn't occur to us when we looked at all of these other arithmetic properties. Natural log of e, oh, what is that? Well, if we had to compute natural log of e raised to the first, we'd say, oh, that's just the exponent 1. Natural log of e, ooh, what is that? Well, now that we look at it in this context, it's obvious that the natural log of e equals 1. But I just wanted to make sure that we knew that. It's something we should know, and it does follow very easily from what we already know, but we just might not think of it when we need to know what the natural log of e is. So just remember that the natural log of e is equal to 1. Before we rush right into the calculus of the exponential function, let's just work with the algebra a little bit. We'll do a few exercises just so that we can gain some skill at using the exponential and logarithm functions to solve equations. Here's one. Solve the equation for x. And what that means is we get x by itself on the left side of the equation, and we get everything else on the right. So here's what I'm thinking. The first thing I want to do is get rid of this 5. I'll divide both sides by 5. And I'd really love to get x on this side by itself, but how do I do that? Right now, this x is trapped inside the exponential function. So as long as I have the exponential function here, I can't isolate x. So I guess the thing is, get rid of the exponential function. And how do we do that? Don't we use the natural logarithm to undo what the exponential function does? and we get the exponent. So here's what we'll do. We'll plug both sides of the equation into the natural logarithm function. Now we see it, don't we? Natural log of e to the x, natural log and exponential functions undo each other, and they leave us just the exponent. Okay? We just solved our exponential function. We just solved our equation for x. And forgive me, that should be in parentheses. Now, what is the natural log of 49/5 equal to? I have no idea. But my calculator knows what it is. So if I really need the value, I'll just get my calculator and compute that. Okay, next example. Somehow I've got to get x by itself. I've got to get rid of the natural log, or at least free x from the natural log. And I've got to get rid of the 2. You know, there are 2 ways that I could do this. Let me do it both ways, just in case we had an inclination to go one way rather than the other. We'll understand that either way is fine. Here's what I could do the first way. Natural log of x squared equals 16. And we know by the properties of logarithms that the natural logarithm of something raised to a power is that power times the natural logarithm. We can bring this exponent down front as a multiplier. Looking good. And we'll get this 2 out of the way. We'll just divide both sides by 2. Oh, this is so easy. All we have to do is get rid of the natural log, and how do we do that? Use both sides of the equation as the exponent for the exponential function. E and natural log of x undo each other. So what we get is x equals e to the 8. I mentioned I could have done this a different way. So let me do it that way right now. What I could have done is I could have gotten rid of the natural logarithm function first, using its inverse, the exponential function. I'll use both sides of the equation as the argument of the exponential function. And e and natural log undo each other. And I get x squared equals e to the 16th. How do I solve for x? Either compute the square root of both sides or do the equivalent thing, raise both sides to the 1/2 power. So this is the same as computing the square root of both sides. And let me ask you something. If I have an expression raised to a power, and I raise that to a power, what do the exponents do? They multiply, don't they? Excellent. So we'll get x to the power of 2 times 1/2 is equal to e to the power of 16 times 1/2. Or x to the first equals e to the 8th. And let me write that a little bit larger. And we get the same thing no matter how we do it, which we should if the properties of natural logarithms and exponents are consistent. By the way, let me just make a side point here in case you haven't had me for Cal 1. There's a certain form of notation that I use about as often as I inhale and exhale. It's this thing right here. I use this all the time. This is mathematical shorthand for implies. Or sometimes that we interpret this as being this implies. This is a universal mathematical convention that we use this symbol in the sense of implies. So whenever we see this, and especially whenever you see me write this, it means implies or this implies. Now let's do some more examples, okay? You know, that's kind of similar to the last one that we did. I think what I'm going to do is I'm going to use the properties of exponents, the properties of logarithms rather. The logarithm of something raised to a power is just that power times the logarithm. So I just moved the exponent down front as a multiplier, a property of logarithms. And then I'll divide both sides by 2. And to free x from the inside of this natural log function, I'll use both sides of the equation as the argument of the exponential function. E and natural log undo each other. They're inverses. So I'm going to get x minus 2 is equal e to the 9th. And that will give me x equals e to the 9th plus 2. That's my solution. What does e to the 9th plus 2 equal? I have no idea, but my calculator does know. And let's do one more example, one more exercise. I guess the first thing I should do is just divide both sides by 10, right? Okay, what should I do next? I have to remove this x from the exponent of e. How do I do that? Don't I use the natural logarithm function to undo the exponential function? I'll use both sides of the equation as the argument of the natural log function. E and natural log undo each other. I get x minus 12 is natural log of 3/2. And then I add 12 to both sides. And there's my solution. Do I know what natural log of 3/2 equals? Not really, but my calculator knows. Okay, let's go on to the calculus of the exponential function. Here's what I want to do. I want to compute the derivative of the exponential function. And I don't think that I can do it directly. I'm going to have to be kind of sneaky as far as how I do this. So watch this. Okay, 1 is the derivative of x. No big news there. But since e to the x and natural log of x are inverse functions, notice how I can rewrite x. I can rewrite x as the natural logarithm of e to the x. And this has the form of the derivative of the natural logarithm of g of x. And we know what that turns out to be. We get 1 over the inner function times the derivative of the inner function. So that means we get 1 over the inner function, 1 over e to the x, times the derivative of the inner function, which I don't know, Well, why is this helpful? It looks like I've chased my tail around and wound up back where I started, namely, I have the derivative of e to the x, and I don't know what the derivative of e to the x is, so what have I really accomplished here? Well, I'll tell you what. Let me summarize what I just accomplished. Wait, I have 1 equals 1 over e to the x times the derivative of e to the x. This is what I want. This is what I want, and I have it in an equation where I know everything else. So all I have to do is solve algebraically for this thing. Let me do that. Here's where we left off. To solve for this thing, I just move 1 over e to the x to the other side of the equation, so to speak. Or algebraically, I take the equation that I have, and I multiply both sides by e to the x. And by golly, these things cancel. So what I have is that the derivative of e to the x is equal to e to the x. Wait a minute, that can't be right. Let's see. I had 1 equals 1 over e to the x times derivative of e to the x. And then I just multiply both sides by e to the x, and the e to the x cancel. So that's 1, that's e to the x. And I get e to the x equals derivative of, son of a gun, I guess that's right. This is a rather amazing fact. No mistake here. E to the x is the function that is its own derivative. A very unique property. Now, before I go on and do some exercises, I'm going to answer a question that one of my students asked me today. And it's a question that I had when I was a student. I'm glad he asked the question because I didn't think about talking about it. But he asked the question, and that opened the door for me to address something that probably you're going to be thinking about as well. And here's what it is. Here's what one of my students asked me today. They said, if the derivative of x to the n is nx to the n minus 1, then why isn't the derivative of e to the x equal to x e to the x minus 1. See, over here, we bring the exponent down front as a multiplier, then we subtract 1 from the exponent. Why don't we do the same thing here? Why don't we bring the exponent down front and then subtract 1 from the exponent? And I'll give a couple of answers. The second one is related to the first, and here's the first answer. Here's my first answer to that question. The reason the derivatives don't look the same, and the reason we don't apply the power rule to the exponential function e to the x, is because x to the n and e to the x are different functions algebraically. X to the n is a variable raised to the power of a constant. A variable raised to the power of a constant. E to the x is a constant raised to the power of a variable. Those are two completely different things. So that's the first reason. Algebraically, they're two different things. They look somewhat alike. These two things look somewhat alike until we analyze what each of them is. Here, the base x is a variable. Here, the base e is a constant. Here, the exponent is a constant. Here, the exponent is the variable. Those are two different things algebraically. And this difference algebraically is going to lead us to the second explanation as to why we don't compute the derivatives of these two things the same way. Here's my second response to that question of why the derivative of x to the n and the derivative of e to the x are not the same. They're computed differently. We noted, first of all, that the functions x to the n and e to the x are different functions algebraically. And because they're different functions algebraically, the graphs of these two functions are different. So why would that affect the derivatives? Well, the derivatives are the slopes of the lines tangent to the graphs. And therefore, the derivatives or the slopes are going to be different because the graphs themselves are going to be different. Let's look at an example or two. Let's consider the function x squared. This is x to the n where n is equal to 2. And here's the graph. We know what that looks like. Here at the point 0, 0 on the graph, this is what the tangent looks like. The slope is the derivative f evaluated at 0. And this is a horizontal line, isn't it? So the slope equals 0. Let's pick another point on this graph. At the point x equal 1, y equal 1. Let me draw that tangent in red. Here's the tangent. And the slope of that tangent is the derivative evaluated at x equal 1. What's the slope of that line? The line's about 45 degrees. So the slope is going to be 1, right? Now let's pick one more point on this graph. Draw the tangent. Here the slope of this tangent here the slope of this tangent is a 45-degree angle too, but it's 45-degree angle going down, so the slope will be negative. So the slope is f prime of -1, which is -1. Now let's compare that with another function, an exponential function. Let's pick a few points in this graph and look at the tangents. At x equals 0, the slope is equal to f prime of 0. And this is about a 45-degree angle, so the slope is going to be 1. Well, we can see differences already. X to the 2 and e to the x at x equal 1. Here, when we have x to the n, the slope is 0. Here, when we have e to the x, the slope is 1. The slopes are different, and the slopes are the derivatives. Let's pick some more points. Let's try x equal -1. This is the point -1, and the y coordinate is 1 over e. The slope is the derivative evaluated at -1. And the slope is positive, but it's very small. I'm estimating that it's maybe about 1/5, something like that. So let's say positive 0.2. So here the slope is positive but small. When x is equal to -1, when we have x to the n, the slope is negative, and it's not that small. So for x to the n, where n is 2, the slope is negative at x equal -1. Whereas here, when we have e to the x, the slope is positive, although rather small. And what about when x equals +1? Oops. Now, I guess I can sort of guesstimate the slope of this if I go from this point on the tangent to this point on the tangent. I'm going over, let me call this 1 unit. So that's a unit, that's a unit. It looks like if I go from here on the tangent to here on the line tangent, I go over -1, and then I go down -2.5. So the change in y is 2.5, the change in x is 1. So when x equals 1, e to the x is approximately 2.5. When x equals 1 here, x to the n is 1. Okay, the slopes are different because the graphs are different, and the slopes are the derivative. So this is another reason why we shouldn't expect that x to the n has its derivative computed the same way that e to the x has its derivative computed. The expression from here to here is just a polynomial. We know how to do this. We're going to get 12x cubed plus 8x minus 7. The derivative of 5 is 0. And remember, we compute the derivative of a sum or difference one term at a time. So we compute the derivative of this term, then this term, then this term, then this term. And then finally this term, which is just e to the x. Let's look at some more examples. Again, we compute the derivatives one term at a time. And to compute the derivative of 3 sine of x, we write down the constant. And then we compute the derivative of the function sine of x. To compute the derivative of 6 cosine of x, we write down the constant. And then we compute the derivative of the function cosine of x. To compute the derivative of 8 e to the x, we write down the constant. And then we compute the derivative of the function e to the x. Let's do one more. Now, what's up with this one? It's a product, right? So we have to use the product rule. I'll call this the first. I'll call this the second. And remember what our product rule says. First prime times second plus second prime times the first First prime is 2x. Second is e to the x. It's the second function verbatim. Plus second prime, the derivative of the second function, that's just e to the x, times the first, x squared. Could I have left it like this? Yes, definitely I could. Typically, we like to put monomials in front of exponentials and in front of trig functions. So I just put the monomial first. If I had left it like that, that would have been fine. Okay, tomorrow we will do some more complicated examples. What happens if we have something other than x up here in the exponent? Well, tomorrow we'll worry about that.